Model parameterization is one of the hardest problems for mechanistic.
Thank you, Daniela.
Sorry, I'm macromodeling.
Yes, I'm macromodeling. Good day to everybody. So we are dealing with parameterization now. So we saw how to model a biochemical system. We saw how to write reactions, and we saw that we need parameters in order to perform simulations. So now we know that sometimes these parameters cannot be collected by means of laboratory experiments. So I will show you some automatic methodologies for the inference of these missing parameters. I didn't expect the screen to be so small, so I'm sorry if you can't read something. In such a case, I will spend additional time explaining what is written, well, it was supposed to be written on the screen. So this is a remote that doesn't work, so okay, this is the outline of our presentation. We'll go back for a brief moment to the modeling of reactions and on the simulation that Dario has already explained very well. Then I will take the problem of parameter estimation with increasingly complex algorithms. And then eventually we'll show you the parameter scalar analysis, which is the final topic of this talk. So reactions can be formalized in this way. We have a set of reactants that become a set of products, and each reaction has a kinetic constant that determines the rate of the reaction itself. So we have a set of chemical species. We have the stoichiometric coefficients that say how many molecules of reactants are involved in the reaction, and how many molecules of the product are involved in the reaction. All this data is mandatory to perform simulation and analysis. All of them. If we miss just one kinetic parameter, we cannot perform simulations, and we can do nothing with our model. So we need those data. And unfortunately, kinetic parameters are difficult to measure, or sometimes are even impossible to measure. Why are they important? Well, as some of you has already pointed out, they have a strong impact from a quantitative and a qualitative point of view. So if we take the same biochemical model, in this case the oscillator that you just shown to us, you can see that by slightly changing a single parameter, we can have a completely different behavior in our system. So we used to have oscillations, now we have a chaotic behavior in the system, which is completely different from the previous one. And if we change another parameter, we have again a completely different behavior. We have a stable system with a slight amount of noise. So we need parameters, and we need very precise parameters if we want to have a faithful reproduction of the emergent phenomena of our biochemical system. So they are important. Since we cannot measure these parameters, maybe we need some indirect measure to perform a parameter estimation. For instance, we can perform experiments in laboratory, and we can collect the time series of the molecular amounts. This can be done often. So we could, in principle, look for the kinetic parameters that once they are inserted into the simulator, they produce a simulated dynamics that is identical to the experimental time series. So we perform the laboratory experiment, we collect the time series of the chemical species, and then we find the kinetic parameters that allows us to perform a simulation that is identical or very well fitting with our target time series. The problem of finding these kinetic parameters is known as the problem of parameter estimation. First, very important, the structure of the model is known, so we know the reactions. We just don't know the kinetic parameters. If we don't know the structure of the model, if some of the reactions are missing, then we have a problem of reverse engineering, which is way more difficult than the parameter estimation. Okay? It's not treated here because it's way too complex, and it would take a single lecture just for that. So we are not dealing with reverse engineering problem here. You can read this if you want to look at the state of the art of the problem. The second important topic is that the initial amounts of the chemical species are parameters of the model as well. So you need the initial amounts of the system. Do you remember the Cauchy problem? You don't need just the ordinary differential equations, you also need the first state of the system to perform the simulation. So you need that. It's mandatory to have the initial parameters. Again, this could be missing as well. If you need to perform the estimation of the initial parameter, this is known as the joint state kinetic constant estimation, but it's too complicated and it's not treated here. Okay? So just the kinetic parameters. So, in principle, kinetic parameter estimation is simple. This is a possible algorithm for the parameter estimation. And if you think about it, it's pretty straightforward. You just collect the time series of the target chemical species, so you perform your laboratory experiment and collect your time series. Then you choose a random vector of kinetic parameters, any vector you want. You perform a simulation with that vector of kinetic parameters, and you compare the target data with your simulated dynamics. So you have your points, and you perform a simulation, and say, okay, how much am I different from the target time series? Well, if I'm different, I just improve the kinetic parameters, and I iterate until I have a good fitting with my target series. It's simple, isn't it? However, it's not clear at the moment how we perform the steps 4 and steps 5. That is, how we compare the two time series and how we can improve, especially, our initial guess of the kinetic parameters. Okay, it's the other one. Very well. So let's start from comparing the time series. What we use to compare the two dynamics is called a fitness function. A fitness function is given a parameterization, it returns a number which quantifies the quality of the fit. The more overlapped are the target time series and the simulation, the lower this value. Okay? So we have a quantification of the quality of our estimate. It's generally defined as a sum of the distances between the two dynamics. So I hope you can see from that. If these are my target time series, I have a simulation and then I calculate the distances of the two curves. And I repeat the procedure for all the chemical species that I can measure, and I repeat the procedure for all the points of my time series. I normalize, use this normalization term here, just to don't give some species more importance than the others. So if some chemical species have higher concentration, they would have a higher weight at the end of this calculation. And I don't want that. I just want to normalize and have a relative distance for all the chemical species. It's not important. What is important is that we are talking about this now. We use this function to calculate how well we are fitting with target time series. So we restated the problem of finding the parameters as the problem of minimizing a function. If you think about it, if this function is 0, it means that we are perfectly touching all the time points for all the chemical species. And that's our goal. So the problem of the parameter estimation corresponds to the problem of determining an optimal solution O, which is the best that we can find. That is, for any possible parameterization in the search space of in the infinite search space of the parameters, the possible parameters, we're looking for the solution that is minimal, that is the lowest as possible, lowest than any other possible solution. That is, a solution cannot be further improved in any way. So it's a minimization problem. The parameter estimation can be seen as a minimization problem. So let's talk a little bit about data.
we hate them.
No, well, this is often the case when we work with biology. So we say, okay, fine. Did you understand my algorithm? Yeah. So show me your data. No, come on. That's the point? A steady state? One thesis? No, come on. We cannot work with that. I don't see the point. So we need, unfortunately, let's say that we need more points than you can generally measure. And I show you an example why this is relevant. So let's assume this is the experimental time series that you collected with your experiments. I'll perform my algorithm for the inference of the missing parameters. And I find parameterization which is good. That is, my simulation basically touches all of them. And we say, okay, it's perfect. We found the parameterization, we can analyze the model. And then eventually you perform another experiment. You say, no, wait. I found out that I have a different dynamics than respect to the simulation you are performing. So maybe there was another parameterization which was able to better fit with the target time series. So the more points you provide us, the more precise and constrained we can perform the estimation. So it's important for us to have a lot of points which force our algorithms to be more precise. Okay, so please collect a lot of points. Okay. This lecture is way better if we do some active teaching here. So if you teach to me the algorithm, okay? Do you want to try this? It generally works. So let's assume that we have to estimate just one parameter now, named K, and here is the fitness function, so the quality of the fit. And now you have this magic tool, magic box. You provide one possible parameter, and the magic box gives you the fitness function. Okay, let's say that we start from here, and the fitness function is here. Okay, we have a random initial point. We know the fitness function. Where do we go now?
Both sides.
What's the next step?
Either way.
Excuse me?
Either way.
Both directions? Okay. So I take a random step into the two directions, and you're here and here, okay? So it's a good idea. We start sampling around and say, okay, it looks like in this direction we are improving because we are, okay? So what's the next step? We have some kind of, arrow that is pointing in a direction. Any suggestions? Come on.
Another point on...
Yes, let's go in that direction. I like it. Okay. We came here, and we iterate, I guess. Oh, shit. Okay. So we found the optimal parameter, isn't it? No, don't break my toy. But yes, I mean, it looks like a reasonable approach for the problem, right?
You don't know what will happen going or not.
Exactly. We don't know what happens on the other side of the world. Maybe there are additional solutions that are even better than that, because it's non-linear. I mean, okay. So what we just explained graphically is called the gradient descent algorithm. We can pick a random initial solution. This was it. And we can calculate the gradient, which is the vector of the partial derivatives of the fitness function. Here was easy because it was just unidimensional, and if you have n dimensions, you have a more complicated situation. it's pointing towards the direction of the greatest increment of the function, so we go in the opposite direction because we want to minimize. Okay? And we are just taking steps going in the direction of towards the minimum. And when we iterate until the gradient is 0, so we cannot improve the solutions in any way. This algorithm is known as gradient descent. If you use an adaptive steps length, it's called Leverberg-Marquardt. Oh, it's important. The surface defined by the fitness function in n dimensions is called fitness landscape. From now on, I will refer to this surface as the fitness landscape. So I can restate what we did a few minutes ago. We are basically walking down the fitness landscape, okay, in the gradient descent. So, yes, this is what we saw. And yeah, it was a local minimum. So shit. And this is a bad situation. Unfortunately, a lot of papers in literature uses the gradient descent because it's easy to implement. But we have no guarantees that we are converging to the global minima of our fitness function. So very often you will find this sentence. So they are using the multi-start approach. So they say, okay, we just pick another starting point in our search space, and we repeat optimization, and we hopefully would not converge to the same solution as before. Which is true, you decrease the probability of converging to the same solution, but you still are not coping with the problem. And the problem here is that the gradient descent algorithm is a strictly deterministic approach. It's going, it's stubborn, it's going in the direction of the improvement of the solution, and it stops when it's no longer improving. But this is not always the best approach to a problem. If you kick in stochasticity, if you use some randomness in your algorithm, it turns out it's way better than before. So gradient descent is good for unimodal fitness landscape, which is not the case of Abelian systems. But what happens if we let the algorithm take a wrong path, intentionally? This is called a simulated annealing. Well, if you invent an algorithm like that, you just end up in science, which is not bad. So, this is an example of the functioning of simulated annealing. As you can see, we have a lot of local minima, but the algorithm is able to converge to the global optimum of the problem. Here you are maximization, non-minimization, but it's the same. So this is the pseudocode of simulated annealing. There is the algorithm described on a high level. Again, we start from a random initial solution, theta, and we initialize an initial temperature because this algorithm is inspired by the cooling of metals. So we pick a random initial temperature, and then we start the algorithm. So we generate a neighbor of our initial solution, a neighbor in a general sense. You decide how the neighbor is calculated. If the neighbor is better, okay, you keep it. But if the neighbor is not better than your current solution, you have an acceptance function. And the acceptance function is based on this probability. So you have a probability of accepting the solutions anyway, even if it's worse. And we have an exponential distribution, and especially the probability of accepting the solution decreases with the temperature. So the higher the temperature, the higher probability of accepting a wrong solution. And the more we cool down the system, the less likely it is to keep your wrong solution. So we accept it anyway, even if it's wrong with this probability, then we update, decrease the temperature, and we iterate until we meet some termination criterion. For instance, the temperature reaches a certain threshold, or the fitness is below a certain threshold, or whatever you like. A number of iterations is the same. Then we return the last theta as the optimal solution. Simulated annealing is able to skip the local minima thanks to this ability of taking wrong paths no matter the quality. And there is a theorem, a very nice theorem, that proves that the algorithm asymptotically converges to the global optimum. Asymptotically is a nice way of computer scientists to say, okay, if you have infinite time, don't worry, you will converge. I mean, I don't have, but you know what. So, the performances of this algorithm, however, are strongly dependent on the functioning settings. So you have to choose an initial temperature which is problem dependent. So you have to try. And you have to choose a cooling factor, and there's a lot of literature about the cooling factors. The initial positions, okay, we have the same problem as the gradient descent. The structure of the neighborhood is not trivial, especially in n-dimensional search spaces. And the termination criteria. So you have to carefully select all of them in order to have good convergence to the optimal solution. Very well.
Sir,
Yep.
I didn't understand the concept of temperature here. I think that how you use it.
Okay. First of all, a suggestion: don't fall in love with the metaphor.
No, that's why.
Because I do, but it's generally wrong. Okay, so it's inspired by the cooling of metals. It turns out that if you heat a metal, you can reorganize the atoms inside the metal, okay? So you have a better crystalline structure at the end when you cool down. So this is the inspiration that Kirkpatrick used for his paper. So you have this higher temperature, which is used to calculate the probability of acceptance, that basically says, okay, at the beginning my system is heated, so I can explore the search space. As I cool down the system by reducing the temperature, I reduce the probability of accepting a wrong solution, so I have a more stable situation and I can converge to I can exploit the local region that I am in. You can see here, it's chaotic at the beginning, but then it eventually slows down and converges to the global optimum. That's the role of the temperature at this time. Okay. Simulated annealing is good, but we can do even better than that. The algorithms that I've shown so far have a peculiarity. They are based on an initial guess of the solution that is improved throughout the iterations. And this may be not the best idea you can came with. In fact, there is a class of algorithms, two additional classes that we see here, that are named population-based methodologies. So instead of having a single solution, you have a population of solutions. You will see that the term population here is as a is connected to the fact that we have literally individuals that are mating with each other, they are crossing with each other, and they are producing new offsprings that are improved with respect to the parents. So, what I'm going to describe now are biome-spiral algorithms. They use a population of individuals. And the individuals represent candidate solutions to our problem, that is the kinetic parameterization. So we have a population of kinetic parameterizations crossing with each other. These algorithms are largely employed for parameter estimation nowadays. And these are two relevant papers that I suggest you to read that investigate the performances of these algorithms. So the first class of algorithms of population-based meta-heuristics is evolutionary computation. Evolutionary computation relies on Darwinian processes. So we have a population of candidate solutions. We have a natural selection, so we select the best fitting individuals, and those best fitting individuals mate with each other. So literally, they undergo a process of crossing of the genomes and random mutations. And examples of these algorithms are genetic algorithms, evolution strategy, and differential evolutions. You may have heard of them sometimes. And this is an example of genetic algorithm applied to the problem of teaching a robot to walk. Okay, so this is the first iteration. the best individual of the first iteration basically falls immediately because it doesn't know how to work. This is 20 generation, I think. I can't read, unfortunately. You see, it's improving, but it's not good either. This is 80 generation. We have a correctly working robot, but it's not elegant, I'd say. And after 1,000 generations, it's perfectly working, and nobody taught him how to walk. It just evolved this capability. Okay, it's outstanding how evolution works on any level, even on algorithms. The other class of bio-inspired population-based methodologies is work intelligence, which exploits the emergent intelligence of groups of agents. You are pretty familiar with the intelligence of ants, but also bats, bees, and birds are able to solve complex problems by using collective intelligence. So you can use that for real. And there are a lot of very important algorithms, for instance, uncommonly, and particle swarm optimization which are inspired by the collective intelligence of animals. In particular, particle swarm optimization was shown to be particularly effective for the problem we are investigating here. So PSO is a stochastic bio-inspired swarm intelligence metaheuristic for global optimization. That's the definition. That's a super capsula for this. It's stochastic because it has some randomness inside of it. It's bio-inspired because, as you can see, it's inspired by the collective movement of birds, starlings especially. It's swarm intelligence. It's metaheuristic because it can be applied to anything, especially parameter estimation. It's global optimization because we do not converge, hopefully, to the local optimum. We can explore the search space. As you can see, the dynamics of these guys here is not different from the dynamics of our collection of particles. Okay, you can see nothing here, but you can see that the movement is similar because this algorithm is inspired by this phenomenon. And Draeger performed a comparison of all the state-of-the-art algorithms for the parameter estimation. It turns out that PSO is the most feasible for this problem. That's why we are looking at it in details here. This is the figure, the main figure from the paper of Draeger. As you can see, he compared gradient descent, simulated linear, genetic algorithms, differential evolution strategy, even the covariance matrix adaptation version, which is considered the state-of-the-art of global optimizations, and particle swarm optimization and tries. And PSO outperforms all the other methods because the average fitness here is the lowest in the case of PSO, always, constantly, consistently, with a low variance. So it's the best algorithm so far that you can use for problem parameter estimation. So how does PSO work? Well, we have particles which represent the candidate solution to the problem, that is kinetic parameters. So each particle is a possible kinetic parameter for your system, but vector of kinetic parameters. So they move in an m-dimensional bounded search space. So we have m dimensions, that is, m is the number of missing parameters of your system. And they cooperate to identify the optimal solution. Each particle is characterized by two vectors, a position in the search space and a velocity in the search space. And the velocity, intuitively, is used to update the positions of the particles iteration after iteration. Naturally, the velocity is not fixed, but it changes according to two attractions. There are two attractions, the social attraction and the cognitive attraction. So, errors. We have a current position of the particle in the search space, which is initially random. Then we have a current velocity, and we have a social attraction. The social attraction is the best position found by the collective, by the swarm, so far. We have a cognitive attraction either, which is the best position found by the particle itself so far. So our particle is torn, is attracted by here and attracted by here. So its movement